Welcome. I'm going to be talking about quantum computers and where to hide from them. I'm Nick Doran. I realized at the last minute I should add a quick About Me slide. I'm MapMeld on Twitter and GitHub. In real life, I'm like a freelance full-stack web developer, usually in the United States, kind of traveling all around. Previously, I've worked at One Laptop Per Child, Code for America, Museum of Modern Art, and do some contributions to open source projects, including OpenStreetMap. And I started seeing these articles everywhere about quantum computing, how it was going to be so big, how it was going to have all these amazing impacts on things, and not just in technical stuff, but like in Bloomberg or The Economist stuff that managers are reading. And I started to wonder, like, what's really going on with that? It reminded me of like reading little rumors about Bitcoin and blockchain back in 2011. So I had these questions and went out and did the reading, and now I've kind of squished them together into a talk. So was starting to wonder, like, okay, why are quantum computers so special? Do they even exist? How would we program a quantum computer if it did exist? And then how do quantum computers affect security and privacy, which I think is like why a lot of people are here for this session. So to recap, why is a quantum computer special? You have to go way back to the beginning where computers kind of went from a vacuum tube, mechanical machine process into these transistors. And that allowed there to be this jump, which most of us will know as Moore's law. So ever since transistors were discovered, transistors have been getting exponentially better and better and better. And so here's this trend line going all the way towards the present. So that looks really exciting. It looks like computers will always be getting better for us. And now we're at this weird point now where people are wondering, will Moore's law come to an end? We've kind of gone in some different directions with multi-core processors and things like that in consumer machines. But in research labs, they're starting to build like the smallest theoretically possible transistors. So after that, there has to be some kind of advance. There could be using photons. They could be using some sort of biological process. There are a lot of different ideas about this. But this talk is about quantum computing. So that's one of the directions that people are really interested in researching in, and it's sort of a really interesting direction for how we could use a different kind of physics to solve computer problems. So in classical computing, that's the term they use for like the computing that we all use now. The classical computing, you have bits. There's 0 or 1. And then in quantum computing, you have qubits, which have other people heard there's kind of it's both 0 and 1 at the same time? Like, does that sound kind of familiar? Seems kind of unuseful for it to be both 0 and 1. So the truth of it is it's sort of in a probability wave between 0 and 1, where if you were to fire a laser at it to measure its position, it would have a certain percentage chance of coming back at 0, certain percentage chance coming back at 1. And if were you to apply some kind of phase shift, then it changes the probability. So there's actually more than one bit of information going on in a qubit when it's in the superposition state. And then these individual qubits can be entangled with each other. So if you have 2 qubits, they can be some level probability from 0, 0, 0, 1, 1, 0, or 1, 1. And then you try to build up entanglement with more and more qubits until you are dealing with a lot of different probability states at once. So if you've taken a physics course that talks about quantum physics, you've probably seen a diagram like this where the photons or things that are in a quantum state exist across this whole range of spaces, and then once they hit a detector, they are at either one or the other. So that's basically, we in the end of the day have to read these values in a classical computer. So when we apply the reading function, it will come back to us as a 0 or 1. So just kind of imagine the two spaces. On the left, you have the quantum space where interesting quantum interactions are happening. And then once we hit it with these detectors, we're going to get a 0 or a 1. And so I think like we feel pretty good about this. Like, this is a model that I can understand. But this is like my favorite Richard Feynman quote: if you think you understand quantum mechanics, you don't understand quantum mechanics. So I would like to say that I have like a popular science level understanding of quantum computers. Like, I was able to follow this diagram to the point of there's something on the left, there's something on the right. But then when you dig into stuff about what are qubits really, you see a lot of diagrams like this, which I do not follow at all, but clearly are very important to turning these little particles into a computational device. So I can't really help you with that, but it's something that people do understand, and they've started building these quantum computing devices. These are a couple of different platforms that exist. And one thing you'll notice right away about quantum computers, even when they have a small number of qubits, they're in these weird tubes and have all these wires coming out. And that's because if you have something that is in quantum superposition, you don't want to have like a photon or an atom or molecule to come in and hit it. So it has to be in a vacuum tube, and it has to be near absolute zero to prevent interference from things around it from moving it out of quantum superposition until you're ready to shoot your laser at it. So people talk about this quantum computing thing as being very revolutionary. Unfortunately, it's unlikely any of these would ever exist like on your desk in your office, unless you already work at a research lab that has absolute zero freezers. It's probably out of range of that. But for that reason, a lot of these startups and people like IBM and Google, which are interested in using quantum computers for their own, hopefully benevolent purposes, they have research labs working on it, and then they would make it available as like a cloud service. So it's not something you should expect to have like on your phone or something like that. It'll just be something that exists as a web service. To get an idea of what's going on in a quantum computer, this is how like a classical computer works, right? Like you start out with these individual gates, and they can be built up into larger logical processors and things that do more interesting things. And so similarly, I have that popular science understanding of this. Like I understand a basic circuit. I understand that code gets compiled and runs on a mainstream computer. And I don't have like a good mental process of that exact jump. But it's important to know, and the basis of it is these small electric gates. And quantum computers also have gates for where qubits interact with each other qubits, or they can have their quantum state run through a gate. So there's several different types of gates. These ones are called H and R. And you can see this is a quantum computer program where 3 qubits are connected to each other and then run through this. And then you also see that the R gate has a number of radians, and that's like a phase shift that's applied to a qubit probability wave when it goes through that gate. So this is sort of like one of the more basic quantum computer programs you could run if you had 3 qubits. And so once you're talking about these theoretical things, you start saying, okay, I saw those things in the tube. I'm seeing articles like this. D-Wave adds 2,000 qubit system. People are saying, do quantum computers exist then? And the answer is they kind of both exist and don't exist at the time. D-Wave is using something called quantum superposition. No, wait, sorry. They're using quantum annealing, which is sort of different from the general quantum computer that people want to build. So it does something, and it seems to be running things in a different way from a classical computer, but it doesn't give us all of the benefits of a general quantum computer that we would like to have. So D-Wave is doing something that's very interesting. Unfortunately, it's not, when you see something saying 2,000 qubits, that would be very exciting if we had it in a general quantum computer, and that's not the case. But over the past year or two, the other quantum computers have gone from just being lab experiments to being something where we're saying, yes, we could have a small program run on one of these devices that's being built in different cases. So IBM will let you simulate up to 56 qubits. That was thought to be impossible. So to give you an idea of how small the number is of qubits that people are working with, IBM can, at this point, simulate 56 qubits. In the cloud, you can get up to 5 qubits, which I believe are run on an actual quantum computer. In Rigetti Computing, which is a startup in Berkeley, you can simulate up to 30 qubits. using, they call it like a quantum virtual machine. And you can set different parameters on the virtual machine to sort of imagine how it'll work on a quantum computer. And later this year, they're supposed to offer these 8-qubit chips, which could be really interesting for running your programs on. So what are you going to do with a quantum computer if you get it? Really, especially since there's so few bits, what can you really run on it? And sort of one of the main applications that scientists are interested in is using it to simulate various properties of atoms and molecules themselves. So kind of interesting way of using like a physical properties of quantum computer to simulate actual quantum effects that you want to get analysis on. So that's really interesting. But how do we go about doing that? So programming the quantum computer, like I told you before, sometimes you're working with a real quantum computer in a lab, and for me, and I assume all of you, we would be interacting with the quantum computer through, for the time being, like this in the cloud virtual machine process. So like I showed you before in that diagram, the qubits interact with each other. When you want to get the result of that, you have the laser fire and save the result into a classical register. And then depending on how it works, you might want to rerun the same program several times to get an idea of probability of it coming out one way or the other. So one language that people have invented for using this is called Quill. So this is Rigetti Computing's preferred environment. So on the left, you'll see sort of like an assembly language type of way of looking at it. And that is what they ultimately send into the quantum computer or the virtual machine. And then on the right, you'll see their library called PyQuil, which is sort of to avoid this assembly language environment and give you a higher level language where you can kind of understand what's going on. And so you can build up programs like this. You can add them together. You notice the assembly program on the left has like a jump and a label. It actually has a goto going on there. And so using Python is a huge advantage because you don't have to think in a goto kind of way. Instead, you can assemble the programs in Python, and then it'll plop out the assembly value at the end. And when I saw this, I said, well, that's cool to have it in Python, but look at calendar, it's 2017, it should be in JavaScript. Also, it's on the web. It seems like a web service. There should be a JavaScript library. So this is my unofficial JS Quill library in JavaScript. So you create the program, you can add different gates to it, and then you can add a command to go from the qubit value, store it in a classical register, and then run it in this kind of callback kind of sort of way. So actually, if you sign up with them, you can get an API key. You can start running things against their virtual machine. IBM has a kind of different approach. They're also using Python, I think, because kind of in the sciences, Python is really popular over there. So this is one of the programs they have, sort of a similar philosophy of telling the program in the beginning how many qubits and how many classical register bits you're going to use. And then they run some different gates on it. And they have several Jupyter notebooks available online, so you can start working with different projects just like that. So why are quantum computers so special then? Right now, they have just a small number of qubits. Why are we anticipating it so much? And the fact is, for over 20 years, people have known that quantum computers are kind of scary. When a quantum computer is built, it's going to be able to break a lot of different prime factorization-based encryption systems. So RSA, ECC are kind of over there. And then Bitcoin is kind of an interesting state where if you have used the public key, then it becomes easier for it to be broken by the quantum computer. Whereas if you have it in like an address and you haven't used it yet, it's more secure. So one theory is we should just, in the Bitcoin world, is they should just move all of their money from one address to another and then only spend it one time. So that's kind of interesting idea with that. So the algorithm that they found for using quantum computer theoretically to break crypto is called Shor's algorithm. And it's actually the diagram I showed you earlier, where you run these qubits through this, but on a much larger scale to deal with much larger numbers. And all this sounds like a supercomputer that's going to solve all of our problems and cause new problems, but it doesn't, like, it's not like perfect. It's not imaginarily it's not able to do impossible things. It's not even able to do NP hard problems any faster than we're able to do today. It's only certain kinds of problems that work better on a quantum computer than a classical computer. So there are a lot of people then interested in building a quantum computer for this crypto breaking purpose. So one of the revelations of the Snowden documents was that they're working to build a quantum computer. I kid you not, they have an underground Faraday cage room working on this quantum computer. And 2016, last year, the NSA said, if someone theoretically made a quantum computer, how should we change the crypto standards now? Like, not saying anyone got there yet, but they seem to be very concerned about it. And so that could be them. It could be China, which has also said they're going to invest millions of dollars into a quantum computer research facility. So this is very interesting. And I want to believe someone out there knows if quantum computer generally exists or not and is breaking codes, but we just don't know yet. So what are we going to do to counteract that? Sounds kind of scary. So a lot of people's idea is if quantum computers are out there and breaking our codes, we should use quantum computers of our own to build them up and encrypt our stuff against them. This is kind of what I call the Pacific Rim kind of theory. We should build a giant mecha robot or something to fight back. Unfortunately, like if you were paying attention earlier, quantum computers have to be in these lab settings, absolute zero, all that. This diagram is completely fake because they're holding it on their laps like a laptop, and there's no way that a quantum computer would work that way. They also have to have a direct line of communication because if anything like transfers or relays a signal, then it's interfering, it's basically capturing the value and then sending it on, and that moves it out of quantum superposition. So the Chinese have done some really interesting experiments with a satellite in space, which makes sense. You beam directly to the satellite, it talks back to you. There's nobody in the way sending messages. But for person-to-person conversations over the internet, quantum cryptography is not like a practical use thing. So what they're going to build instead is post-quantum cryptography. So there's several different types of post-quantum cryptography using several different classes of math problems. And the reason that we're not using these today is that, like you saw RSA, ECC, those are things that people understand very well. They've been implemented in pretty much every server library out there. And we know that they work, or we know that bugs have been shaken out over time. Whereas if you release a new library, it might look really good, and then if it's never been used before, there are bugs in it waiting to be discovered. So in post-quantum cryptography, sort of the thing people are really excited right now is called lattice-based cryptography. And in lattice-based cryptography, you have these multi-dimensional grids. You move the points somewhere in that dimensional space, and then the decryption process sort of moves them back into that space. So these are some of the other options. For something like RSA, it would have to be much, much, much longer. So that's not particularly interesting to, like, in terms of just efficiency of using cryptography. Other ideas are using quadratic equations, using hashes, because those are, and then you would have a key that tells you, expect this from the next hash. And so it would go on for a while, and then you would need to renew your keys, or something called McEliece or Goppa codes. But everyone seems to love lattices. It's pretty well efficient. Every time that they've evaluated it, it looks like it's effective against both quantum and classical computers. Right? You have to check that this isn't going to expose your device to being hacked by regular computers in the meantime, right? So the lattice-based computing is the basis of something that's gone through several iterations, and now is called something like ring learning with errors. So if you hear like all these different ideas and someone's written a paper about ring learning with errors, you can trace it back through several steps to, oh, okay, they're talking about a lattice problem. And so it's able to do symmetric and asymmetric encryption. So let's get this going on the web. So in HTTPS, the server and client agree on a cipher that both understand. So a server could say, hey, I'm going to start using lattice-based crypto. Are you up for that? And if the browser is into it, then they can communicate using that system. So right now, AES 256 is kind of the toughest that's generally offered by the server and accepted by the client. When quantum computers come out, it will be halved in. It's as similar as if you're using AES 128 today. So only like half the length of the key. So that sounds pretty good. Problem is a lot of crypto is not on AES 256. A lot of crypto right now, HTTPS is using AES 128. And the other problem is that the initial key exchange step is something that the quantum computer could grab, and then this whole step of doing AES 256 would not protect you more. So kind of what's going on now, Google is experimenting with lattice-based encryption. They're using that ring learning with errors process that I talked to you earlier, and the paper that they're basing it on is called A New Hope from Star Wars. And so they've run it out on some of their servers, and some Google Chrome users are experimenting with this. And they still use AES as like a backup. So if someone were to discover a hole in lattice-based crypto, they would say, don't worry, we also encrypted all of your stuff with one of the more classical AES ciphers in the meantime. So hopefully as this gets used more and more by Google and other companies, people will try to break it, maybe break it, and improve it over time. So yeah, it's A New Hope, and it's included in Boring SSL, which is their open SSL fork, and lingering with errors. Okay, so that's the web part. What about encrypted email? Does anyone use encrypted email time to time? Using GPG, PGP, something like that? A few people. Yeah, well maybe you've seen it, like, have you ever gotten a message on a message board and it's followed by this really long block of random letters and numbers that's their signature? So yeah, so that's using GPG, really useful for encrypted email. And it's using these same algorithms and ciphers which are vulnerable to being hacked by, or being broken by quantum computers. So there's this guy, Mirek Kratochvil, who I've only talked to on GitHub, so I never was like, how should I say your name at conferences? But anyway, he has a project called CodeCrypt, which is not professionally verified in any way, but his goal of this was to use a couple of different encryption systems to mimic GPG. So the same commands that you would send to GPG on the command line, you could send to this over the command line. So the encryption process is using the McEliece Goppa code system, and the signing of a document is using a different hashing function from GPG. So as a result, you don't just need one public key and one private key. You need to have public and private keys for encryption and public and private keys for signing. So makes things a little bit more complicated there. I don't know why he decided not to use lattice-based, but it's just something that lattice-based is very new, so my guess is that he started this project a while ago. So one problem that I had with this is that it is modeled after the GPG commands and storing the keys in a keyring, but it has a different output. So what I decided to do is I use this Enigmail plugin, which you can find in Firefox Thunderbird for sending GPG emails, pointed it at CodeCrypt, and then added some additional JavaScript code that would allow you to use CodeCrypt in place of GPG. So just as an experiment, or I don't know if this counts as trolling, I don't know, I sent it out to the Enigmail list, just asking for advice, like, are people interested in post-quantum encryption? And I got this really great response from Robert Hansen from the Enigmail GPG mod saying, right now there's no use for quantum-resistant crypto, absolutely none. And at the end he says, we have no plans to make Enigmail run on the USS Enterprise's duotronic or isolinear systems. He seems to know a lot about IT support on Federation starships. And we also don't have plans to support post-quantum cryptography, smiley face. So we were cool. I like that this happened because it gave me an idea of we don't need to change someone else's system, but it's interesting to know about, we don't need to change Enigmail to do this kind of obscure case, but it's interesting to know some other people were interested and wanted to use this, and it's possible to migrate the plugin to work the same way, but with a different command line tool. Yeah. So kind of ongoing open questions. When will quantum computers exist in the state that they're not just lab experiments, but people are like more routinely running chemistry experiments, crypto processes in real life. Because as far as I've heard, I know that they're building quantum computers. I haven't heard of a case where someone has successfully used the quantum computer as they exist today to break codes. That's all a theoretical thing. It will work. It's just more of a thing of the quantum computers that exist today aren't ready for it. Someone asked me a good question at an event, like, do brains use quantum computation? This is kind of an ongoing theory of like how we have consciousness, or we're able to think better than computers through some kind of quantum effect. And it turns out the people that believe this have a completely different idea of how quantum computing works in our brains, and it's not related to the kind of superposition entanglement that we're talking about in this case. Another open question is, will this new kind of crypto, including lattice-based encryption, is that reliable? Is that going to survive testing out in the world as it gets used more? And it's sort of an open question. I think you can expect there to be more limitations found or different problems in different implementations, but that's the sort of thing that happens in crypto today, and we just sort of gradually improve over time. I saw a talk by someone from Akamai where he said it usually takes about 5 years for a security standard to spread out to the general use across the web. And he's also heard that there's about 5 years until quantum computers become more practically available for researchers. So he was saying that the time is right now to think about what standard do we want to see out there on the web. It's sort of an open question. It probably would be lattice-based, but I wouldn't be surprised if in the meantime someone came around and proposed something else. So kind of an interesting development. About a year ago, Shor, Peter Shor, who had released that initial algorithm for breaking prime factorization using quantum computer all the way back in 1994, published a paper or preprint on archive.org saying that he had found an efficient quantum algorithm for breaking lattice-based crypto. So in the post-quantum crypto Twitter sphere, this is a huge event. Everyone was like, oh no, lattice-based crypto is broken. It was retracted within 3 days. So there was like a little error in the code here. And so we know that for now it's safe. But there are people working to break it, and it's very possible that people will find that. So there are people looking. They'll have some kind of way of discovering that over time. If you're interested in learning more about quantum computing, like I did not like go and take a special course on this at all. There's some community events out there, and they usually post videos online. So Rigetti Computing has been doing a Bay Area meetup every couple of months. I don't know if anyone else is from the US actually. But you could start up your local meetup if you know someone who seems to know a lot about this. pqcrypto.org has a list of different events. There's going to be a like summer school and conference. Like they did one past few summers, so I think they'll do another one in the Netherlands this summer, or this coming summer. And then there's a PQ Crypto conference in April in Florida. So thanks for coming to the talk. You can look at pqcrypto.org. A couple books that I would recommend is Post-Quantum Cryptography, which is about like 5 years old at this point, but has a lot of summaries and goes into more computer science-y kind of explanations of the different alternatives that you could use for post-quantum crypto. And Scott Aronson is a professor who keeps this blog, and he also has published a book called Quantum Computing Since Democritus, which goes way back and also covers lots of different cases, people saying, how do you know it's possible? Is there some information? There are a lot of different arguments that he talks about there. Or you can ask me on, I'm MattMeld on Twitter and GitHub. If you have, I think we have time for questions now, but if you have questions in the future, I'll try to answer them or send you some resource of someone who actually knows more details about that. But yeah, thanks. Okay, so do we have time? I think we have time for questions. It's quantum computers. It's okay if you don't know everything. Yes. So right now it's very difficult to build the computers. Like theoretically, they've known for over 20 years different algorithms that they want to run on quantum computers. But okay, one thing that's difficult is error correction. So right now, if you were doing something with hardware, you would have individual bits. And then in case something gets messed up with one of the bits, you have like an error checking bit, 0 or 1, to evaluate it. With quantum computers, as soon as you compare it to a classical bit, you have to bring it out of quantum space by measuring it. So they were saying we go through all these processes, and at the end, it's encountered all of these errors, and we build up errors over time, so we don't know if the output is reliable. So more recently, one of the reasons that quantum computers have been getting more research from Google, Microsoft, et cetera, IBM, et cetera, is they've developed sort of a quantum circuit for doing error correction in that quantum space. So little things like that, which have been solved on classical computers a long time ago, are sort of more slowly being developed in this space. And there's still a lot of noise. Like on the virtual machine, you can decide how much noise you want to have in your environment, but in real life, you wouldn't be able to control these little errors and things that pop up. I think someone else have a question? Okay, if no one else has a question, like you can just come up and talk to me afterward. Okay, thank you so much.